class, now we are on Module 7. In Module 7, we are going to focus on Chapter 7, and we're going to be learning about the quantum mechanical model of the atom. Before we can get to the quantum mechanics portion, we need to review light, and specifically the nature of light. Now, light can have both wave-like and particle-like properties. And the quantum mechanical model, why is this going to be useful for us? Well, it explains how electrons exist and behave. So it lends us some insight on properties of atoms. So in chemistry, we care a lot about reactions, right? Our reactions moving forward to make some products. Well, to understand those better, when we learn about the quantum mechanical model, we apply it so that way we focus on why there are certain periodic patterns in our periodic table. And it also lets us understand reactivity. Okay. Now, visible light is a type of what's called electromagnetic radiation. Now, electromagnetic radiation, it is composed of oscillating electric and magnetic fields. So you have an electric field component and a magnetic field component, and notice they're perpendicular to one another. We're not going to focus so much on this. When you get to physics, you learn about that in more detail if you have to take physics. But when we talk about waves and light acting wave-like, where you have two different types of waves. So there are what's called a traveling wave. These are like your ocean waves, and we can picture that. Ocean waves. And we have what are called standing waves. So those are like, we can picture a guitar or stringed instruments. And when you pluck the string on a guitar, you know it's held by its two ends. And we know that we get some oscillations with our guitar strings, right, to make the different sounds. So waves can be described magnetically, and that is by sine and cosine functions. Now, we're not going to do any of this math, especially for folks who haven't taken that yet, that type of math. But we know that they can be described by our sine and cosine functions. What I would like the class to know about wave properties and what we focus on is we're going to look at the term frequency. So frequency, it looks like a V, but it has a little hook. It's kind of hard to see here. And this is called nu. And it could be described by 1 over time, so 1 over s. Another way to write this is s to the minus 1, and the hertz. And another property for waves is the wavelength. And the symbol for wavelength is lambda. So lambda here, okay, so lambda here is usually measured in meters, nanometers, or what's called the angstrom. Now the angstrom, it's actually a letter from the Swedish alphabet, but we know for the angstrom, which will have a new conversion factor here, is going to be 1 angstrom is equal to 10 to the negative 10 meters. Okay, so still it still relates to the metric system. Now let's define our wave properties, frequency and the wavelength. We talked about what the units are. Now frequency is defined as the number of crests per unit time. Okay, and I'm going to show you a picture on the next page on what that looks like. And a wavelength is defined by one complete cycle of a wave. One cycle of the wave. And again, I'll show you what this looks like on the next page. I'm just defining it right now. And we know that our frequency and our lambda are going to be inversely proportional. So if one goes up, the other one's going to go down. Okay. Now, other wave properties are the amplitude. This is the height of the wave from the midline. And we have what's called a node. A node is a point where our wave crosses our axis and the wave function equals 0. So that's going to equal 0. All right, so I'm going to go ahead and now I'm going to point out everything that I've just said. So in this picture, so notice here, I'm looking at A. Now the wavelength, well, we can actually have it, so let me draw a little picture as well. So I'm going to focus on A. But if I draw one wavelength, that could mean from this portion to this portion, so that's one complete cycle. And when it's at the top of our wave, this is called a crest. The bottom here is called a trough. That's called a trough. Now, I mentioned before, let me put the line in the middle, just like that picture. I mentioned what a node is. A node is where it will equal 0, or a wave function equals 0. This becomes important later on, but here, and I'll explain it more, but here where it crosses the axis, this means that that wave function will equal 0. Okay, so if we notice, if I'm looking at this picture, I'm focusing on A again, I notice that the wavelength for A is longer than my wavelength for B, which is A is still longer than my wavelength for C. So as you go from A, B to C, the wavelength is getting shorter and shorter. And what do you notice about the number of crests per unit time? So the frequency is the number of our number of crests, right, per unit time. So all of these still have the same time. Notice in A, I've got 1, 2, 3 crests, and number B, or letter B, 1, 2, 3, 4, 5, 6, 7, and then many in C. So as the wavelength is getting shorter, our frequency is getting higher. So then again, it reinforces that those are indirectly proportional. So here we have a formula. C equals lambda times nu. So C is the speed of light, and here I'm showing it with several decimal places, but a lot of the times we're just going to use 3 times 10 to the 8 meters per second, so that's its velocity, right? Now, to put things in perspective a little bit, the speed of sound is 340 meters per second. So it is 1,000,000 times slower than the speed of light, and that's why we actually see the fireworks before we hear them. And so let me point out this formula down here again, our lambda, and this is just another way to write it. I'm just rearranging it. This is our wavelength. This is the speed of light. And it's a constant, it's never going to change. And then this is our frequency. Okay, so usually 1 over s to the minus 1. Wavelength is in meters, nanometers, and it could also be in angstroms. Okay, so let's talk about amplitude a little bit. So we haven't really talked about the height of our waves. Now, if we have a higher amplitude, that means that if I'm looking at this curve is going up here, and that's higher than this wave down here. So the distance between the axis and the height of the crest, that's going to give you your height of your amplitude. So if you have a higher amplitude, that means you have brighter light. And if you have a lower amplitude, you have a dim light. Okay. All right, so now we have a relationship. When we talk about electromagnetic radiation, we want to bring up with the spectrum. So many of you have seen this spectrum before. Here, what I want to point out first is that we're going to look at our relationship between energy, our frequency, our wavelength. Okay, so let's look at our wavelength. So we have the wavelength going in this direction, and we have the frequency going, it's saying it's increasing in the opposite direction. So that just reinforces again that they are indirectly proportional. And let's go over the spectrum itself. So here we have radio frequency. So that's an example is our cell phones use radio frequency. And then we have microwaves, and we all are used to microwaves. We cook in our microwaves a lot. Then as I go to the left, or as the frequency increases in this direction. I have infrared next. Now infrared, that's when objects are hot objects, and many of you know that's also when we can use night vision goggles, right? So those night vision, or if they're you're going ghost hunting, you can go ahead and use the night vision goggles, or you're looking for Sasquatch, right? So here, that would be the infrared. Now notice the visible part that's next. Look how tiny that is. Well, what they're trying to show here is that visible region. We can blow it up, and we notice that in this area here. But look at what a small part of the spectrum it is. Okay, now if I look at the visible spectrum, what I want you guys to know is that you have 400 nanometers here. So blue light will have 400 nanometers. And over here with the red light is 750 nanometers. So I want you to know that. Know those two values. And then refresh everyone's memory that visible light, we can use the Roy G. Biv, right? So red, orange, yellow, blue, or red, orange, yellow, green, blue, indigo, and violet. So our Roy G. Biv. Now after we, as our frequency increases over here, we have the ultraviolet light. So we know about that in sunscreens. And then we have X-rays. We know that those are used for medical, the medical industry. And then we have gamma rays over here. So that's like our sun and our stars. So I'll just put like the sun and the stars. Now, some animals, oh yeah, this is just interesting. Some animals or insects can see the UV light. That's why those electronic bug zappers work, right? So they can actually see it. We can't see it, of course, so we are only able to see this little tiny, out of all the different kinds of, all the different frequencies available, wavelengths, we are only able to see in this visible region. So again, a very small portion of our spectrum. So we have a wide range of radiation, and it's a continuum, right? So our frequency increases, and let me go back to this. So our frequency increases as we go from radio to gamma. Now our gamma rays, if we start here, our wavelength starts to get, it's really short here, but starts to get longer and longer as we get to the radio frequency. So our wavelength for radio frequency is going to be quite long. Now how does that relate to energy? So we know that wavelength and frequency is indirectly proportional. Energy goes in the same direction as frequency. So, and most of us understand that gamma rays will have a much higher energy than a radio wave. I mean, gamma rays, if we're exposed, will kill us, but we're exposed constantly to radio frequencies. So energy and frequency goes in the same direction, and wavelength will go in the opposite direction. Okay, so let's go ahead and let me finish writing in for the visible region. Again, I've repeated it, but it's an extremely small part of the spectrum. So I want to do an